my dinner, in fact, that I will be sharing with you guys. But hello and welcome. Hello and welcome indeed. Good evening, good morning, good night, good afternoon. My chickpeas are bursting actually. Give me 1 second. I'll be right back. There we go. There's the microwave. Oh, whoops. Oh, whoops-a-daisies. So today I'm quite hungry. I did not eat a dinner. And in fact, I ate sort of a later lunch / breakfast. And so indeed, I am kind of really hungry now, and therefore I will be eating my chickpeas with you. I will be eating my chickpeas with you. And in fact, chickpea break is here. Hello, Ver. Hello, Nathan. How are you doing? You can see me eat some chickpea live with you, and then we will pick up from where we were. Brief History of Time by Stephen Hawking. And in fact, we will pick up where we left off, which is elementary particles, particle physics, matter particles, force particles, all the particles. We are here. We are indeed here. Fixing my face. Sachi! Sachi Mama is crying. Hi, Sachi, what's wrong? Sachi let out a cry. I'm not sure. Hi, baby. Hi, baby. Sachi Mama just wanted a little bit of attention. Mama's eating, baby. No Fuji. Fuji is licking the chickpea can, which is actually not a good thing at all. So we were talking about, where's the cheese? You're right. You're right. I missed the cheese. Here, let me go get it. So we were talking about matter particles and force particles. We were just about to talk about the 3 fundamental forces that are better understood. And then we were going to get into gravitation as well. We're still on that same chapter. Elementary particles, both matter and force particles. We will pick up there once I finish my chickpea break, which is just a bowl of chickpeas, so shouldn't take long. Hi, Nathan. Chickpea break says, finally a chickpea break. Sounds good to me. Thank you. Where's the cheese? I'm going to go get it. Quarks, up quarks, and down quarks. Exactly. Up, and down, down, and up. Those are protons and neutrons. Those were made up of quarks that we talked about. So you remember. You do remember. Thank you so much. Thank you so much. I'll eat a couple chickpeas dry because that's how hungry I am. Oh. Very hot. Hello, King Prime. Hello. Indeed. How is everybody doing? Let me get, shall I add some blue cheese to this? You know, this blue cheese is from a salad. Thank you. Welcome one, welcome all. Welcome to my dinner. After which I will continue the particle physics live lecture. But, oh my gosh, I put the ghee in the fridge, so it has become extremely solid. Welcome one and welcome all. Thank you so much for being here. If you put something in the chat, then I will be reading it out and saying your name and everything. I'll see King Prime says, what's up? Hello, King Prime. Awias says hello. Hi, Awias. Diametris says, I intend to consume 2 chairs in 4 years. Oh, okay. Very nice. Should I add a little blue cheese? It says chunky blue cheese on it, on this. I don't know if this is a good idea or not, but I will try it. So tonight you will see me eat the chickpeas live because I am very hungry indeed. And I love the chickpea meal. I love it. It's actually quite good. I don't know if you've tried heating up chickpeas and eating it with Spicy Chili Crisp by Lao Gan Ma, but it's actually very good. I add ghee to it. I added a blue cheese to it. I added, this cheese, Parmesan, to it, and I will be eating this right here, right now. Right here, right now. Lots of cheese right there. So how is everybody doing? Hello, Hawaiius, or no, Hawaiius. Trying something new is worth a try. Yes. Oh, thank you. You are most supportive of my chickpea consumption. Oh, interesting taste. The blue cheese. Okay. Hello, Dora Madness. Heavy-handed with the parm, just the way I like it. Yep, I do love me some parm. In fact, I didn't get enough. Okay, so how is everybody doing? Are you ready? Do you remember where we were with the particle physics? And thank you for reminding me about the cheese. Can we get 10 likes? Chickpea break says chickpea break with blue cheese. Sup, Var? Yes, Var is here. Doro is here. Hello, Doro. How was work? I think I need a spoon, not a fork. $20. Yes. I'm gonna get a spoon. 20 likes is right. Doro is correct. Let's try to get 20 likes. These are chickpeas. I'm enjoying this chickpea break. Let's get 20 likes. Work was very exhausting. Taking a personal day tomorrow. Amazing. Hell yeah. What you eating? Chickpeas. Thank you for being here. That's what I ate. Oh. Oh my gosh. That would be amazing if I got a super chat for eating. Then I'll teach you physics. Oh my god. I'm hungry. So good. My twin. Am I your twin, Miles? I'm sorry. I have to eat. I'm so sorry. Oh. You guys saw me eating the chickpeas before, right? I finished everything. The chickpea dish is immaculate. Oh yeah, I love this dish. This is great. This is amazing. Oh, this is the most amazing meal on earth. Right here. Oindri stars. It's just amazing. It's warm. It's just right, you know? It's just right. Yeah, where's Reese? Here, share the live. Ooh, I forgot to share the live. Oh, Reese can't see until I share it because he doesn't get notifications. Indeed, I must share the live. He's my boy, but he has the hits. Oh. Oh no. Oh, that's not good. A chickpea picture for my picture? No, I like your picture. Ver, keep it. Keep it going. I like the picture you got for the profile called Chickpea Break. I do like it a lot. A lot. Okay, I'm going to share the live on my channel. Keep it. Keep it. I'll see. We are live. Okay. Okay. I like it too. Aw. I think now he'll see it. Come and goon. I read that as come London. I shared it. He loves chickpeas. It's true. Any day now he's gonna adopt this diet. Any day now. This is what he really needs. I burst one chickpea in the microwave though. I'm having a chickpea break with a chickpea break. Indeed, and that photo, amazing. Oh, today, 2 of my neighbors said that they're moving out. So, I think it's you guys. You did something. You can see Suji's zoomies. I blame you. You made me sing. You made me sing. And now look. People are leaving the building. People are selling their units and leaving the building. She overdid a single chickpea in the microwave. That's right. That's correct. Thank you for liking the live. Thank you for liking the live. Please double tap. Please double tap. Can we get 10 likes? Hello, Ram Candy. Please do like the live. Thank you. That's true. It's 20 likes. Can we get 20 likes? Oh my god, I'm almost done. This is the best meal of my entire life. Right here. Pop-Tarts, hello. Thank you for liking the live. How are you, Pop-Tarts? Ooh. Maybe I'll eat a Pop-Tart. Maybe I'll eat a Pop-Tart. I have Pop-Tarts. Oh my god. I finished all the chickpea. Oh, this was lovely. Oh my god. Just the most amazing meal of my life. Let me get some ginger beer. Oh my god. Wow. Wow. Just wow. Just wow. You remember Dora Madness? Just amazing. My. Oh, I'm gonna get ginger beer, then we're gonna start with the particle. Hope you enjoyed my dinner. Wow. I'm gonna lick the bowl. It's so good. It's so good. It's so good. This was chickpeas. It's done now. I finished. Empty bowl now. Put a little ghee in it, just a little. Not as much as I would have liked because it was too frozen. She has a friction walk. I have these slippers that I wear, which you can hear. Yes. Yes. I added blue cheese today. Have you had fish sticks? Probably have. I probably have. Who cares? Who cares? Fish sticks. I didn't have fish sticks at home. I eat what's available. You know what I mean? I eat what's available. I eat what's right here in the bowl. But fish sticks sounds good. Are you buying? If you're buying, I'll eat fish sticks. This dream is powered by chickpeas. Get it? Exactly. We only eat food out of a microwave. Who cares? Exactly. With the chickpeas, I don't need anything. I don't need to kill a fish. I don't need to eat. I don't need to kill a fish. Chickpeas is enough for me. If you want me to eat fish sticks, send a super, which covers the fish sticks. I'll probably buy more chickpeas with it though. Oh, it's so good. Chickpeas and ginger beer. Chickpeas and ginger beer. People who have money don't have money though. The money is doing things. So the money is not available to buy chickpeas with. You know what I mean? Right now, my balance is like negative 3,000. Negative 3,000. You don't. Hi, Jonathan. Where is Jonathan? Where's the first message? Jonathan says hi. Hi. More content plus new smart microwave. Is she drunk? No. This is just ginger beer, non-alcoholic. Oh, this is fantastic. Oh, this is fantastic. Just amazing. The most amazing thing I've ever had. All right. You guys, thank you so much for all your support today. Thank you for letting me eat the chickpeas. I was very hungry. I was very hungry. Just very hungry. Now, I will be going back to the particle physics. See right here. So we talked about the matter particles. Yeah, Batman, can you please like the live? Give us 10 likes. Make it 20. Give us some likes right now. In fact, Batman, have you played video games? I don't play video games. I don't have the time for video games, unfortunately. Indeed, no. Indeed, no. I haven't watched any movies and I haven't watched video games or played video games. She literally works on telescopes. Aww, 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 how nice. Okay, so can you please like the live? I don't know what happened. I see 9 likes now. I need 10 likes right now and then 20. What do you mean Super Bowl commercial? Okay. Batman, do you want to send a super? Do it. So yesterday we got started with this particular topic of elementary particles, which of course includes both matter and force particles. Now we will take a look at some of these forces. So the first category is the gravitational force. This force is universal, that is, every particle feels the force of gravity according to its mass or energy. Gravity is the weakest of the 4 forces by a long way. It is so weak that we would not notice it at all were it not for 2 special properties that it has. It can act over very large distances, that's a big property, and it is always attractive. That's not necessarily the case for all of the forces. So gravitation is kind of special. Acts over very large distances and is always attractive. This means, oh, Fuji is eating something. Fuji? Okay, no, he is not. Fuji, I'm watching you. This means that the very weak gravitational forces between the individual particles in 2 large bodies, such as the Earth and the Sun, can all add up to produce a significant force. The other 3 forces are either short range or are sometimes attractive and sometimes repulsive, so they tend to cancel out. In the quantum mechanical way of looking at the gravitational field, the force between 2 matter particles is pictured as being carried by a particle of spin 2 called the graviton. Yes, exactly. This has no mass of its own, so the force that it carries is long range. So if the force particle doesn't have a ton of mass, in this case no mass, then it can go long range. The gravitational force between the Sun and the Earth is ascribed to the exchange of gravitons between the particles that make up these 2 bodies. Although the exchanged particles are virtual, so when these 2 bodies are exchanging particles, that particle being exchanged is virtual. Yes, graviton. It's a virtual particle being exchanged, or lots of gravitons being exchanged between the Earth and the Sun. But in that particular case, it's considered to be virtual. Actually, if you don't make a direct measurement of a graviton, you can't quite say that you have measured one. Now, of course, we did start to see gravitational waves being measured within the last decade, which is really, really exceptionally exciting because we got some of the first direct measurement of gravitational waves. So although the exchanged particles are virtual, they certainly do produce a measurable effect. They make the Earth orbit the Sun. Real
Real gravitons make up what classical physicists would call gravitational waves, which are very weak and so difficult to detect. And then he said they have not yet been observed, but actually they have been observed now. At the time of writing this book, maybe they weren't. And in fact, that's right. This book was published first in 1988, and then it got a 10-year revision. So definitely since that time, we have seen gravitational waves. So we will keep going. Thank you for liking the live. Can you please share the live, like the live, subscribe, do all that. Do all that. What is happening? Can you please like the live? Like, share, subscribe. I'm gonna share it again because I don't see the usual crowd. Thank you for the hearts. Thank you so much. Thank you for coming to the live. Welcome, welcome, and thank you for the hearts. And Chickpea, I'll make you a mod. There we go. I made Chickpea a standard mod. So Chickpea, your color will change. I think it should be a blue color now. I'll say that we are starting the particles. Yay, Chickpea Brick has turned blue, so you're a mod now. Thank you. Okay, we'll keep going. So that was about the gravitational force. The next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. So we know which types of particles interact with the electromagnetic force. It's the charged ones. Electrons, protons, well, within the protons, it's really quarks, but not the particles that have no charge, such as a graviton, or in fact, not even a neutrino. So we've mentioned the particle called neutrino, which is a type of lepton, and it's actually chargeless. So it does not interact with the electromagnetic force. It only interacts through the weak force, another type of force that we'll talk about. But for now, let's see what the electromagnetic force is, which I'm sure many of you will be familiar already, because it's just basically all the charged particles will interact through that. So the next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. And remember, quarks is what makes up the neutrons and protons. It is much stronger than the gravitational force. The electromagnetic force between two electrons is about 1,000,000, million, 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 million. So one with 42 zeros after it times bigger than the gravitational force. Yes, so quarks make up protons and neutrons. So the protons and neutrons are subatomic particles in the nucleus of atoms, and those particles each are further made up of even smaller particles called quarks. Why can his troll name get a mod but not mine? Yours can too. I thought you changed it back and forth. Yours can get a mod. The water break? I thought that was you. I thought that was the this you. Is it not? Thank you for coming to the live. Welcome to the live. Thank you. Thank you so much. Thank you for being here. Yes, I will make you a mod. Thank you so much. Thank you for being here. Welcome to the live. Please do like the live. You're listening. Good. Oh my god. There, water break. The OG in retro. Yes, water break is now a mod as well. Okay. So the electromagnetic force is all blue. This really is Doro. Watch this. Hello? I hope it's Doro. Back again. I love how water break is proving their authenticity and authority. So the electromagnetic force is much stronger. It is 1 with 42 zeros after it times bigger than the gravitational force. However, there are two kinds of electric charge, positive and negative. So we will talk about that. So the difference will be a couple different things. So we will talk about that. So between up and down quarks. So remember how gravitation is a type of force that is only attractive. But in the case of electromagnetic force, of course, depending on the charges, the opposite charges are attractive, but the same charges are not. They repel each other, but there is still a force. So there are two kinds of electric charge, positive and negative. The force between two positive charges is repulsive, as is the force between two negative charges. But the force is attractive between a positive and a negative charge. So the case with electromagnetic forces is not just attractive or just repulsive. Depending on the charges, it is either attractive or repulsive, which again is different. And also we know that the force is much greater than the gravitational force. So, a large body, such as the Earth or the Sun, contains nearly equal numbers of positive and negative charges. Thus, the attractive and repulsive forces between the individual particles nearly cancel each other out, and there is very little net electromagnetic force. However, on the small scales of atoms and molecules, electromagnetic forces dominate. The electromagnetic attraction between negatively charged electrons and positively charged protons in the nucleus causes the electrons to orbit the nucleus of the atom, just as gravitational attraction causes the Earth to orbit the Sun. So neutrinos are very small. If you're looking for something small, neutrinos are a type of lepton. They're in the lepton family of particles that is very small. But as far as whether quarks further break down or not that we know. Okay. Yes, thank you so much for asking questions about the science. So the electromagnetic attraction is pictured as being caused by the exchange of large numbers of virtual massless particles of spin 1 called photons. So now remember, light is an electromagnetic wave. Hey, Oendry, says Stephen. Stephen, hello. Light is an electromagnetic wave, and the particle nature of light is photons. So all of these electric charges having the force between them, the positive charges attracting the negative charges repelling other negative charges or positive charges repelling other positive charges. This type of thing basically means that they are exchanging virtual massless particles of spin 1 called photons. The force between them is carried by photons. Or sorry, the interaction between them is carried by photons, is the force interaction particle in this particular case. Yes, particles act as waves, and yes, perfect. That's true. Love it. I love some condensed matter facts. So basically, that's what we are saying is being the facilitation of the force between these particles in the case of the negative charges, the positive charges, electron and proton, proton, neutron. Well, actually, yeah, proton and neutron, and then proton, proton. All of this, as far as the electromagnetic force goes, it's the photon that is actually being exchanged. However, when an electron changes from one allowed orbit to another one nearer to the nucleus, energy is released and a real photon is emitted, which can be observed as visible light by the human eye. So, if it has the right wavelength or by a photon detector, such as a photographic film. So you can even see this type of jump in the form of a light basically being released, detected, whatever. Equally, if a real photon, so when you actually detect it, like if you see light, then you've detected it, then you've detected a photon, right? So in the same way, one could basically argue that if we saw gravitational waves coming from far, far away, which is what we did a few years ago, several years ago now, I think it was either 15 or 17, might have been 2017, then that's basically like saying, yes, we've measured a graviton. But I don't know though. Check the facts on that, whether people consider that to be the same as measuring a graviton or not. But basically, if you see a light because something happened in the atom where the electron went to a different orbit and released basically some photons or a photon, then that is basically saying, yes, that's a real particle, that's a real photon that we just detected. But when the force carrier, the force is carried by photons and there's exchange of virtual particles like the virtual photons, then that's considered a virtual photon. So yeah, thank you so much. Thank you for being in the live. Can you please like the live? Can we get 20 likes? Can we get 20 likes? So again, equally, if a real photon collides with an atom, it may move an electron from an orbit nearer the nucleus to one farther away. This uses up the energy of the photon, so it is absorbed. So photons can be emitted or absorbed. And when that happens, we say that's a real photon. When photons are exchanged between two charges, we call that virtual photon. Thank you. Welcome, and thank you so much. And please do like the live. Now we'll go to the third category. So we will talk about the quarks. I saw some questions about quarks. We will get back to it in a bit. Let's keep going. I think you will enjoy the next part. So we'll talk about quarks. The third category is called the weak nuclear force. So we've covered gravitational force, sort of the nature of the gravitational force, electromagnetic force, and now we'll go to the weak force. Very interesting. The third category is called the weak nuclear force, which is, so by the way, weak force, weak nuclear force, same thing. Strong force, strong nuclear force, same thing. Like sometimes we call it weak force, sometimes we say weak nuclear force, sometimes we say strong force, sometimes we say strong nuclear force, but those are the four. that we know of. Gravitational force, number one. Number two, electromagnetic force. Number three, weak nuclear force. And number four, strong nuclear force. So now we'll talk about the weak nuclear force, which is responsible for radioactivity and which acts on all matter particles of spin 1/2, but not on particles of spin 0, 1, or 2, such as photons and gravitons. So weak nuclear force is another force that acts on particles of spin 1/2. And now remember that matter particles are all spin 1/2. The electrons are spin 1/2. Neutrinos are spin 1/2. The protons and neutrons are spin 1/2, even though they do break down into further subatomic particles called quarks. The weak nuclear force was not well understood until 1967, when Abdus Salam at Imperial College London and Stephen Weinberg at Harvard both proposed theories that unified this interaction with the electromagnetic force, just as Maxwell had unified electricity and magnetism about 100 years earlier. So remember, people used to think of electricity and magnetism as two separate things. They didn't have to be part of the same theory, but we understood that they are, and Maxwell and others did the work to figure out that electric and magnetic fields are actually the same. They turn into each other. They're the same thing, kind of, and part of a more unified theory of electromagnetism. So same thing kind of happened here. So here, these people, once again, it's Abdus Salam at Imperial College London and Stephen Weinberg at Harvard, both proposed theories that unified this interaction with electromagnetic force. They suggested that in addition to the photon, there were three other spin 1 particles known collectively as massive vector bosons that carried the weak force. So now we get some other additional bosons. Yes, thank you, Steve. Oh, perfect. So far we've kind of talked about the graviton as being the boson associated with the gravitational force. We've talked about the photon as being, for sure, associated with the electromagnetic force, such as charges attracting each other or repelling each other, depending on the type of charge. Now we meet some more bosons, okay? So these are called massive vector bosons, and they carry the weak force. These are W plus, so pronounced literally W plus, and it's written as a big W with a plus superscript. W minus, again, big W with a superscript minus, and Z naught. So that is Z, big Z or Z with a superscript 0. So W plus, W minus, and Z0 or Z naught, those are the names of these new massive vector bosons that we're meeting in the context of the weak nuclear force. So each had a mass of around 100 GeV. So we talked about the EV earlier. I think yesterday we talked about the electron volt. That was a unit of energy, electron volt. And now we've got the giga electron volt. So GeV, like a gigabyte. Similarly, giga electron volt. So again, these are W plus, W minus, and Z naught, and each had a mass of around 100 GeV, where GeV stands for giga electron volt or 1,000 million electron volts. The Weinberg-Salam theory, so these are the two people, Weinberg and Salam, theory exhibits a property known as spontaneous symmetry breaking. This means that what appear to be a number of completely different particles at low energies are in fact found to be all the same type of particle, only in different states. At high energies, all these particles behave similarly. The effect is rather like the behavior of a roulette ball on a roulette wheel. At high energies, when the wheel is spun quickly, the ball behaves in essentially only one way. It rolls round and round. But as the wheel slows, the energy of the ball decreases, and eventually the ball drops into one of the 37 slots in the wheel. In other words, at low energies, there are 37 different states in which the ball can exist. If for some reason we could only observe the ball at lower energies, we would then think that there were 37 different types of balls. That's a pretty good analogy. In the Weinberg-Salam theory, at energies much greater than 100 GeV, the three new particles and the photon would all behave in a similar manner. So the three new particles, or the three new bosons that we just kind of mentioned, W plus, W minus, and Z naught, don't have to be thought of as such a different thing from the photon, which is why they can be kind of united with electromagnetic theory. It doesn't have to be so different, especially when we consider higher energies. So once again, in the Weinberg-Salam theory, at energies much greater than 100 GeV, the three new particles and the photon would all behave in a similar manner. But at the lower particle energies that occur in most normal situations, this symmetry between the particles would be broken. W plus, W minus, and Z naught would acquire large masses, making the forces they carry have a very short range. So if the force particles have very high mass, then the force they carry becomes more shorter range. You will see how this affects these types of forces. For example, the electromagnetic force is carried by photons, and as we know, they are massless. So electromagnetic force is very long range. So at the time that Salam and Weinberg proposed their theory, few people believed them, and particle accelerators were not powerful enough to reach the energies of 100 GeV required to produce the real W plus, W minus, and Z naught particles. So we're saying that these particles have this mass, but if you're not able to sort of detect them in a high enough energy environment, which is the particle accelerator, because they just don't go to those energies yet, then you can't really prove it out. And until it's proved out, until it's really discovered in an experiment, measured, it's not real. So that's why people didn't believe them yet. Oh, thank you, Steve. Love that comment. So, however, over the next 10 years or so, because as you know, we can definitely reach energies over 100 GeV now for a while. So over the next 10 years or so, the other predictions of the theory it's like 14 TeV center of momentum energy that we can achieve at the Large Hadron Collider, if I'm not mistaken. So basically, we're definitely past GeV levels of being able to do things. Okay, so over the next 10 years or so, the other predictions of the theory at lower energies agreed so well with experiment that in 1979, Salam and Weinberg were awarded the Nobel Prize for Physics together with Sheldon Glashow, also at Harvard, who had suggested similar unified theories of the electromagnetic and weak nuclear forces. So, at the time when they're proposing this, not very many people believed them, and the particle accelerators were not powerful enough to reach the energies of 100 GeV, which is required to produce the W plus, the W minus, and the Z naught. But at this point, of course, we can reach those energies, and also they many of their predictions of the theory at lower energies agreed very well with experiment, which is good. And they got the Nobel Prize for physics. Not far from bed. Today was wild. Hello, combat sports. Hello, Chickpea Break. Hello, Doro. Hello, Combat Sports. Hello, everybody. How are you doing? How are you? How are you? How are you? So then we have Sheldon Glashow as well, who got that Nobel Prize with them. The Nobel Committee was spared the embarrassment of having made a mistake by the discovery in 1983 at CERN, European Center for Nuclear Research. I think combat sports country is from there, sort of. Of the three massive partners of the photon with the correct predicted masses and other properties. So, so basically, they gave the Nobel Prize after confirmation at lower energies. If they did not find these bosons, then that would be embarrassing. But they were spared of having made a mistake in 1983 when the three massive partners of the photon with correct predicted masses and other properties was actually discovered. So the W plus, the W minus, and the Z naught were all discovered in 1983 at CERN. Thank gosh. So then Carlo Rubbia, who led the team of several hundred physicists that made the discovery, received the Nobel Prize in 1984. So this is the person who led the team of the several hundred physicists that made the discovery, as in they worked on the experiment, which is also very, very, very difficult. Along with Simon van der Meer, the CERN engineer who developed the antimatter storage system employed. Goodness. It is very difficult to make a mark in experimental physics these days unless you're already at the top. The fourth category. So now we go on. So this is about the weak nuclear force. They found the W plus, the W minus, and the Z naught. All was well because they were predicted a while ago, but they had not reached high enough energies in the accelerators to really discover them. But then lots had kind of agreed at lower energies. Hello, Stephen. How are you? So they went ahead and gave the Nobel Prize, and it was good, but it was a relief when we did discover them. And it is no joke to create these experiments that would support such a discovery. That is a very hard experiment to do. So hundreds of people were involved, and the important people were given the Nobel Prize as well. Sleepy but good. You? Good. Good. I think we'll wrap up a little early today. And we'll keep going for now. I'm a little sleepy too, to be honest. Oh, I love Steve's comments. Solve for X. Oh, I love it. Steve's doing some algebra. Let him. It's okay. Do some algebra, Stevie. Go ahead. Go ahead. She really did go to the bathroom and came back after 4 whole days? What? Okay, the next category is the strong nuclear force. So we just spoke about the weak nuclear force. Now we will talk about the strong nuclear force. Okay? The fourth category is the strong nuclear force, which holds the quarks together in the proton and neutron. So you might be wondering, what is the deal with the proton and neutron being made of quarks? What is kind of keeping the quarks together in order to make protons and neutrons? And the force that keeps those things together, the quarks, to make neutrons and protons is the strong nuclear force. So holds the protons and neutrons together in the nucleus of an atom. It is believed that this force is carried by another spin 1 particle called the gluon, which interacts only with itself and with the quarks. The strong nuclear force has a curious property called confinement. It always binds particles together into combinations that have no color. One cannot have a single quark on its own because it would have a color: red, green, or blue. Instead, a red quark has to be joined to a green and a blue quark by a string of gluons. So red plus green plus blue equal to white. You can go back, you can rewind the live, and we just covered the W plus, W minus, and Z naught. So you can go back in the live. So such a triplet constitutes a proton or a neutron. Another possibility is a pair consisting of a quark and an antiquark, red plus anti-red, green plus anti-green, because quarks have colors, blue plus anti-blue, things like that. Oh, hi, Sachi. There was a noise above me and I didn't know what it was. Such combinations make up the particles known as mesons, MESONS, which are unstable because the quark and antiquark can annihilate each other, producing electrons and other particles. Similarly, confinement prevents one having a single gluon on its own because gluons also have color. Instead, one has to have a collection of gluons whose colors add up to white. So the color is something that to consider when we build up, for example, a proton or a neutron. Such a collection forms an unstable particle called a glue ball. The fact that confinement prevents one from observing an isolated quark or gluon might seem to make the whole notion of quarks and gluons as particles somewhat metaphysical. However, there is another property of the strong nuclear force called asymptotic freedom that makes the concept of quarks and gluons well defined. At normal energies, the strong nuclear force is indeed strong, and it binds the quarks tightly together. However, experiments with large particle accelerators indicate that at high energies, the strong force becomes much weaker. And the quarks and gluons behave almost like free particles. So if you have very, very high energy, the quarks and gluons will behave like free particles. So we have a photograph here of the collision between a high energy proton and antiproton. Thank you for liking the live. Enjoy. The success of the unification of the electromagnetic and weak nuclear forces led to a number of attempts to combine these two forces with the strong nuclear force into what is called a grand unified theory. This title is rather an exaggeration. Remember, Einstein was working on a grand unification theory where he really wanted to have a theory that explains quantum mechanics, relativity, and everything. That is more of the grand unified theory of the 20th century. That we have spoken about, but this is sort of another type of unification that people were trying. This title is rather an exaggeration. The resultant theories are not all that grand, nor are they fully unified, as they do not include gravity. So without unifying gravitation, it would be a little bit of an exaggeration to call something a very grand unification theory, maybe a mini grand unification theory. Nor are they really complete theories because they contain a number of parameters whose values cannot be predicted from the theory, but have to be chosen to fit in with the experiment. Nevertheless, they may be a step toward a complete, fully unified theory. The basic idea of GUTs is as follows, as was mentioned above. The strong nuclear force gets weaker at high energies. On the other hand, the electromagnetic and weak forces, which are not asymptotically free, get stronger at high energies. So that's the big difference. At some very high energy, called the grand unification energy, these three forces would all have the same strength and so could just be different aspects of a single force. So this is all to say, are these forces sort of the same thing? Are they the same basic thing, just existing at different energy regimes or something like that? The GUTs also predict that at this energy, the different spin one-half matter particles like quarks and electrons would also be essentially the same. Oh, I just remembered something. That at this energy, the different spin one-half matter particles like quarks and electrons would also all be essentially the same, thus achieving another unification. So they're saying basically if you go to this type of energy, even quarks and electrons might be basically the same, which would be very interesting. The value of the grand unification energy is not very well known, but it would probably have to be at least 1,000 million GeV. So one could imagine where in a very extreme environment, maybe I'm just spitballing, maybe at the beginning of the universe, when things were hot, dense, excited, all that, it could be that these were all the same at that time. So maybe that's something that we will hear about. The present generation of particle accelerators can collide particles at energies of about 100 GeV, and machines are planned that would raise this to a few thousand GeV. But a machine that was powerful enough to accelerate particles to the grand unification energy would have to be as big as the solar system and would be unlikely to be funded in the present economic climate. So they're saying, he's mentioning that there are some limits to the funding needed for these types of experiments. Thank you for coming to the live. Can you please like the live? Thus, it is impossible to test grand unified theories directly in the laboratory. However, just as in the case of the electromagnetic and weak unified theory, there are low energy consequences of the theory that can be tested. The most interesting of these is the prediction that protons, which make up much of the mass of ordinary matter, can spontaneously decay into lighter particles such as anti-electrons. So that's pretty cool. The reason this is possible is that at the grand unification energy, there is no essential difference between a quark and an anti-electron. The three quarks inside a proton normally do not have enough energy to change into anti-electrons, but very occasionally one of them may acquire sufficient energy to make the transition because the uncertainty principle means that the energy of the quarks inside the proton cannot be fixed exactly. The proton would then decay. The probability of a quark gaining sufficient energy is so low that one is likely to have to wait at least a million, lots of millions, one followed by 30 zeros. This is much longer than the time since the Big Bang, which is a mere 10,000 million years or so. Thus, one might think that the possibility of spontaneous proton decay could not be tested experimentally. However, one can increase one's chances of detecting a decay by observing a large amount of matter containing a very large number of protons. If, for example, one observed a number of protons equal to 1 followed by 31 zeros for a period of 1 year, one would expect, according to the simplest GOT, to observe more than one proton decay. So you have to kind of do these interesting experiments to find some of these predictions. It's not easy. It's not going to be given to you so easily. Oh, hi, Baji. Let me show you Baji real quick. He is sitting here in a very cute pose. Also, let me put all the food away. 1 second. Thank you. No what? No bath? What does this mean? What does this mean? So then, even though it is very difficult to observe spontaneous proton decay, it may be that our very existence is a consequence of the reverse process, the production of protons, or more simply of quarks, from an initial situation in which there were no more quarks than antiquarks, which is the most natural way to imagine the universe starting out. Matter on the Earth is made up mainly of protons and neutrons, which in turn are made up of quarks. Thank you for liking the live. Can we get 20 likes? There are no antiprotons or antineutrons made up from antiquarks, except for a few that physicists produce in large particle accelerators. We have evidence that from cosmic rays that the same is true for all the matter in our galaxy. There are no antiprotons or antineutrons apart from a small number that are produced as particle-antiparticle pairs in high-energy collisions. If there were large regions of antimatter in our galaxy, we would expect to observe large quantities of radiation from the borders between the regions of matter and antimatter, where many particles would be colliding with their antiparticles annihilating each other and giving off high energy radiation. Thank you. Thank you for liking the live. We have no direct evidence as to whether the matter in other galaxies is made up of protons and neutrons or antiprotons and antineutrons, but it must be one or the other. There cannot be a mixture in a single galaxy, because in that case we would again observe a lot of radiation from annihilations. We therefore believe that all galaxies are composed of quarks rather than antiquarks. It seems implausible that some galaxies should be matter and some antimatter. Now comes a great question. Why should there be so many more quarks than anti-quarks? Why are there not equal numbers of each? It is certainly fortunate for us that the numbers are unequal, because if they had been the same, nearly all the quarks and anti-quarks would have annihilated each other in the early universe and left a universe filled with radiation, but hardly any matter. There would have been no galaxies, stars, or planets on which human life could have developed. Luckily, grand unified theories may provide an explanation of why the universe should now contain more quarks than anti-quarks, even if it started out with equal numbers of each. As we have seen, these theories allow quarks to change into anti-electrons at high energy. Thank gosh. They also allow the reverse processes, anti-quarks turning into electrons, and electrons and anti-electrons turning into anti-quarks and quarks. There was a time in the very early universe when it was so hot that the particle energies would have been high enough for these transformations to take place. But why should that lead to more quarks than anti-quarks? The reason is that the laws of physics are not quite the same for particles and antiparticles. Not the same. It's not an equal playing field for particles and antiparticles, if you were wondering. It is not the same. It's not the same. It's not an equal playing field. Up to 1956, it was believed that the laws of physics obeyed each of three separate symmetries called C, P, and T. The symmetry C means that the laws are the same for particles and antiparticles. The symmetry P means that the laws are the same for any situation and its mirror image. The mirror image of a particle spinning in a right-handed direction is one spinning in a left-handed direction. The symmetry T means that if you reverse the direction of motion of all particles and antiparticles, the system should go back to what it was at earlier times. In other words, the laws are the same in the forwards and backwards directions of time. But in 1956, two American physicists, Sung-Dao Lee and Chen-Ning Yang, suggested that the weak force does not in fact obey the symmetry P. In other words, the weak force would make the universe develop in a different way from the way in which the mirror image of the universe would develop. The same year, a colleague, Chen Xiang Wu, proved their prediction correct. She did this by lining up the nuclei of radioactive atoms in a magnetic field so that they were all spinning in the same direction, and showed that the electrons were given off more in one direction than another. The following year, Lee and Yang received the Nobel Prize for their idea. It was also found that the weak force did not obey the symmetry C. That is, it would cause a universe composed of antiparticles to behave differently from our universe. Thank you for liking the live. Nevertheless, it seemed that the weak force did obey the combined symmetry CP. That is, the universe would develop in the same way as its mirror image if, in addition, every particle was swapped with its antiparticle. However, in 1964, two more Americans, J.W. Cronin and Val Fitch, discovered that even the CP symmetry was not obeyed in the decay of certain particles called K mesons. Cronin and Fitch eventually received the Nobel Prize for their work in 1980. A lot of prizes have been awarded for showing that the universe is not as simple as we might have thought. There is a mathematical theorem that says that any theory that obeys quantum mechanics and relativity must always obey the combined symmetry CPT. In other words, the universe would have to behave the same if one replaced particles by antiparticles, took the mirror image, and also reversed the direction of time. But Cronin and Fitch showed that if one replaces particles by antiparticles and takes the mirror image, but does not reverse the direction of time, then the universe does not behave the same. The laws of physics, therefore, must change if one reverses the direction of time. They do not obey the symmetry T. Certainly, the early universe does not obey the symmetry T. As time runs forward, the universe expands. If it ran backward, the universe would be contracting. Thank you for being here, and thank you for liking the live. Much appreciate. And since there are forces that do not obey the symmetry T, It follows that as the universe expands, these forces could cause more anti-electrons to turn into quarks than electrons into anti-quarks. Then, as the universe expanded and cooled, the anti-quarks would annihilate with the quarks, but since there would be more quarks than anti-quarks, a small excess of quarks would remain. It is these that make up the matter we see today, and out of which we ourselves are made. We're made of quarks. Aww. Thus, our very existence could be regarded as a confirmation of grand unified theories, though a qualitative one only. The uncertainties are such that one cannot predict the numbers of quarks that will be left after the annihilation, or even whether it would be quarks or antiquarks that would remain. Had it been an excess of antiquarks, however, we would simply have named antiquarks quarks and quarks antiquarks. Grand unified theories do not include the force of gravity. So all of this stuff that we have been saying about the things being unified at a higher energy, this does not include gravity. This does not matter too much because gravity is such a weak force that its effects can usually be neglected when we're dealing with elementary particles or atoms. However, the fact that it is both long range and always attractive means that its effects all add up. It's always attractive. It's long range and always attractive. So its effects all add up. So for a sufficiently large number of matter particles, gravitational forces can dominate over all other forces. This is why it is gravity that determines the evolution of the universe. For a sufficiently large number of matter particles, gravitational forces can dominate over all other forces. This is why it is gravity that determines the evolution of the universe. Even for objects the size of stars, the attractive force of gravity can win over all the other forces and cause the star to collapse. My work in the 1970s focused on the black holes that can result from such stellar collapse and the intense gravitational fields around them. It was this that led to the first hints of how the theories of quantum mechanics and general relativity might affect each other. A glimpse of the shape of a quantum theory of gravity yet to come. Thank you so much for liking the live. Can we get 20 likes? So that was that chapter, Elementary Particles and the Forces of Nature, by Stephen Hawking in this book, Brief History of Time. The next chapter is called Black Holes. He himself, like he just said, worked on black holes, which is, of course, a step in stellar evolution towards the death of the star. Really, star dies. If it has large enough mass, it can become a black hole, and he himself worked on black holes and gave us new insights into that whole thing. So, very interesting indeed. Very interesting indeed. So, yeah, pretty interesting. The quarks, anti-quarks thing, and the, here is the proton and antiproton collide at high energy, producing a couple of almost free quarks. Here's that picture. Next, we will talk about black holes from this book. Let me know if you have any questions from the stuff that we just covered, which is the particle theory, the particle, elementary particles, and the force carrier stuff. So both matter particles and force particles. Let me know what you think. Let me know what you think, and if you have any more questions, and I'll come back and read your comments in 1 second. Actually, I will read all your comments so that I can see what questions you might have asked. And then I have to go to the bathroom. This is it. The bathroom break. Is Doro here? The chat is really quiet, so I don't know.
I'm so very sorry. I thought that this live was killed because of the. I got a phone call and I thought that killed the live, but it didn't. I'm so very, I'm so very sorry. Can we get 20 likes? Let me see all your comments. Wait a minute. Oh no, this is not the. Hi, I'm here to say goodnight. Steve, thank you so much. Thank you so very much. Thank you so very much for typing and chatting. Steve, good night. Good night, Oindri. Good night, chickpea break. I see all the comments. Aww. Dora says good night. Batman, you're here. What's up? I came back to say goodnight. How are you doing? I came back to say good night. Good night. Chillin' and killin'. Wow. Good night. Can you like the live? Thank you for the hearts. How come I have less likes now? Thank you. Good night. I kind of want a snack now. I'm hungry. I'm hungry. Kind of want a snack. No. I'm hungry. Let me make a clip saying, thank you so much, everybody, for being here. Really appreciate you. Thank you for listening to Elementary Particles and Forces of Nature. Tomorrow we will talk about black holes. Please join as soon as you see the live. Go live. Please look for your notifications. Please like, share, and subscribe. Please be on time. And thank you so much indeed. Love you all. Good night. Good night. Good night. Good night. Good night. Good night. Mwah. Good night. Good night.